This module is going to deal with extinction angle, and anisotropic versus isotropic minerals. Alright, when you rotate the stage, when you have a thin section on your stage, you'll notice that most mineral grains change color as the stage is rotated, and that the grains go black 4 times in 360 degrees rotation, exactly every 90 degrees, like this. These are called anisotropic minerals, and most of the minerals that you'll encounter and that we'll look at are anisotropic minerals. There are some minerals and other materials that don't behave this way. Glass, a few isotropic minerals, liquids like fluid inclusions, and gases that you might see as air bubbles stay black in all orientations. This is an example. It looks like a 6-sided garnet. Garnet is isotropic. So when you rotate the stage, it stays extinct the entire time. These minerals are isotropic. Here's an example of a garnet, another nice little euhedral 6-sided garnet in XPL. And if I rotate the stage, it's going to stay extinct the entire time. The other examples of isotropic things that you're likely to encounter are bubbles, and you can identify bubbles because they're bubbles in the epoxy because they're nicely round. Or you might have a hole in the thin section, meaning when you polish the thin section, little bits of the rock may be polished away, or at the grain boundaries, it got so thin that there's nothing there, and all you're looking through is glass. There's no rock on that thin section. It's just the glass of the glass slide. And you'll see holes. And oftentimes you'll see this little pattern like this that tells you that you're looking at a hole. And that's always going to be isotropic. So, glass, those air bubbles, any fluid inclusions, and isotropic minerals like garnet are always going to be extinct in XPL. In an anisotropic mineral, one property we observe is the extinction angle. The extinction behavior is a function of the relationship between the optical axes, the indicatrix, that I'm not going to worry you with that, but the optical axes, how light passes through the mineral, how those are oriented relative to the crystallographic orientation, so the crystal axes. In some minerals, the C-axis, the long axis of the crystal, here's quartz, for example, is in line with the optical axis, and that's denoted by Z here. If the C-axis, if the crystallographic axis is in line with the optical axis, you see parallel extinction. And that means that the mineral will go extinct when that long axis is parallel to the north-south or east-west crosshairs in your microscope. You see inclined extinction, this angle between the crystallographic axis C and the optic axis Z, when the two axes aren't aligned. And I'll show you what these mean. All uniaxial, uni meaning one, uniaxial minerals show parallel extinction like the quartz. So when the long axis is parallel to the north-south crosshair, it's going to be extinct, and then every 90 degrees, so east when it's oriented east, south, and west as well. And orthorhombic minerals, and we'll get to the crystal systems, show parallel extinction, and that's because this crystallographic axis and the optical axes, the indicatrix, coincide. So here's an example, orthopyroxene. The long axis, we can see it's not a long crystal, but we see these cleavage planes that denote the long axis. Those are parallel to the north-south crosshair right there, and this is in PPL. We cross the polars, put in that upper polarizer, and you see that that same grain, when it's oriented north-south, is extinct. It's a uniaxial mineral. The monoclinic and triclinic minerals, so different crystal systems, have optical and crystallographic axes that don't coincide, and those have inclined extinction. So, and that the actual angle that the mineral goes extinct is helpful to identify which mineral you're looking at. So in this case, we've got a clinopyroxene, and the CLIN, the clino, prefix to that name indicates that it's an inclined extinction. That's helpful. This is in cross polars there on the left. We rotate the stage about, let's say, 45 degrees, and that same crystal is now extinct. It's not in line with the north-south crosshairs, it's not in line with the east-west crosshairs, it's got an inclined extinction, and we can measure that angle with the goniometer on your stage. So there's the angle that you would measure from. You would measure from the north-south crosshair to wherever the maximum extinction is. Now, I've been talking about crystal systems and various optical properties and using the crystal system names just to show you that the crystal systems here, isometric, hexagonal, tetragonal, orthorhombic, monoclinic, triclinic, all are classes based on the length of the crystallographic axes and the angle between those crystallographic axes. And I'll let you peruse this on your own time, but the isotropic minerals like garnet are all isometric, this class. Uniaxial minerals are hexagonal or tetragonal, and biaxial minerals are orthorhombic, monoclinic, or triclinic. So what you learned today, anisotropic minerals go extinct every 90 degrees, isotropic minerals are always extinct in XPL, and with anisotropic minerals you either have a parallel extinction or an inclined extinction. Now I'd like you to watch videos of thin sections 8 and 100, and then complete the quiz on extinction and isotropism.